представляем лекцию Нобелевского лауреата по физике Барри Бэриша, работающего в Калифорнийском технологическом университете в Беркли, Университет Калифорния. Название лекции «Исследование Вселенной с помощью гравитационных волн».
I'm going to talk to you today about gravitational waves. As most people know, gravitational waves were discovered about 3-4 years ago. Today, I'm not going to, sorry, let me start over. Sharing's not working.
Yes, Barry, we don't see your presentation now.
You don't see it. Hold on. Let me start over again and pull it up. Sorry about that. Okay, you should be able to see my screen if I share now. Now you can see my screen or not?
No, we can't. Do you have rights for screen sharing? Well, now we see.
Now you see it?
No, we have. We see your desktop. Can you please full screen your presentation?
I thought I was sharing it.
We see your desktop, not a full screen presentation. Maybe.
Okay. Let me. Can I just get out and call back?
Okay, let's try it.
So I'm gonna start all over again. Somehow I've got more than one screen here.
we can start now.
Wait a second, make sure I can advance because I don't see it on my screen. We see it on your screen, but my screen doesn't have the whole view. I don't see the slides on my screen. Could I just go out and set my thing up again? Because somehow
представляем лекцию Нобелевского лауреата по физике Барри Бэриша, работающего в Калифорнийском технологическом университете в Беркли, Университет Калифорния. Название лекции «Исследование Вселенной с помощью гравитационных волн».
General relativity to see if it's very much in agreement with Einstein's equations, which it is. However, it's also in agreement with some alternates, variants, which are yet to be pursued. But today, I'm not going to talk about general relativity that much, and I'm not going to do the tests of Einstein, but rather talk about how gravitational waves give us a new way to look at the universe. Everything we know about the universe essentially comes from studying electromagnetic radiation and electromagnetic waves. And what we can do in the future, we hope, and are beginning to do, is to actually do gravitational waves in other ways. So let me reflect back first at what has given us significant advances, the most significant advances in astronomy in the last 50 or 100 years. In the 20th century, if I wanted to characterize the one advance that helped move astronomy forward, there were many great instruments and singular discoveries, but the one thread that goes through everything and the one feature that helped the most in studying electromagnetic spectrum or astronomy is that we learned how to not just look in the optical wavelength like classical astronomers did, but look at all the different wavelengths. So I show here the wavelength of light, which can vary from very, very long wavelengths, like the radio, all the way up to very, very high energy gamma rays. And basically, what has been done, and I illustrate that on the right by just showing a picture of the Crab Nebula, is to look at the same phenomenon or the same objects and look at them not just in the visible, but in all the different wavelengths that you might be able to detect them. So what we've done in astronomy, what we've done is be able to actually study by seeing the phenomena that create light in different wavelengths, what we call multi-wavelength astronomy. And I would characterize that, instrumentally at least, as the big advance of the 20th century. We've gone beyond that even. What we've seen already in the 21st century is that we've seen not just looking at different wavelengths, but how to combine instruments that are in different places in the world. The dramatic example of that was done last year when radio telescopes, about 7 of them from around the world, were combined together. They were never meant to be combined together. The information from them was combined together to give one effective radio telescope that was basically the size of the Earth. By doing that, they were able to image a black hole. And this was rather big news. In order to get the resolution to image a black hole, you needed an instrument more or less the size of the Earth. And by using all these different instruments, that pulled them together. We're doing the same thing in gravitational waves, and that is combining the information from instruments that are spread around the world. So that's what I'm going to aim for. And the next frontier beyond that, now that we've gotten to combine instruments, we combine different frequencies, is to combine different messengers. In this case, we like to call it multi-messenger astronomy. And on the left is just pictures of a lot of different instruments that do astronomy, from the Kobe satellite to Chandra, to a lot of instruments which we've heard about. And together they've enabled us to study the electromagnetic spectrum. Now we can add to that if we can see the same phenomenon, and I'll show you one very nice example of that already. We can look at a completely different way that waves are sent from some phenomena in space, that is by gravity instead of electromagnetism. And that's detecting the same phenomenon also in gravitational waves. There's a third possibility, and that is the interactions that are happening in a phenomenon in space also have particle interactions or elements or nuclear physics. And that produces also a marker that tells us what happens in terms of the phenomenon on microscopic levels, and that would be neutrinos. So what we're entering is a century where what we'll start to see is looking and understanding the most profound observations in our universe by looking at a combination of information from electromagnetic radiation, from gravitational waves, and from neutrinos. We can't barely do it yet with neutrinos, but that'll improve. And with gravitational waves, we have one very nice example, which I'll show you today. And gravitational wave detectors are going to get better and better as we move into this century. And this whole way to do astronomy, looking at different messengers, will start to evolve. That's my main message today. And now I'm going to talk about gravitational waves some, and how we actually have combined in one observation gravitational waves and electromagnetic waves. So first, let's reflect back on gravitational waves. We all learned about gravity from Newton. And in 1687, he wrote the Principia. In the Principia, he explained how gravitational pull is inversely proportional to the distance between what's pulling on each other, two objects, shown here as M1 and M2, but times the product of the two masses, and a constant that's the strength of the gravitational field. This is what he called universal gravity, and it worked for everything from the apple falling out of the tree to the moon going around the earth, or any other gravitational phenomenon, including the tides that come in from the ocean. That theory is maybe the most successful theory of all time. It survived from 1687 until a new theory of gravity was proposed by Einstein in 1915. I'll show you why we needed a new theory of gravity. It doesn't mean that Newton's theory was incorrect, but it means we have to look at gravity in a more sophisticated way to describe certain effects that Newton's theory could not describe. So Newton's theory is basically based on the formula that I wrote, while Einstein's theory is a theory of geometry. It's based on space and time being unified into a four-dimensional space-time. This is basically the way he viewed how nature really works, and that gravity itself distorts the space and time around it, and that's how it works. In 200 and some years after Newton's theory, we had basically no cases that were in violation of Newton's laws. Everything that was measured for 200 and some years worked, except one possible exception, and that was the orbit of the planet Mercury around the sun. The planet Mercury, I'll remind you, is our planet that's closest to the sun. and has an orbit that's very elliptical, as I've shown in this picture. And as it goes around, it gets pulled by not just the sun's gravitational field, but as it approaches the sun by the positions of all the planets and moons and so forth. And it comes back to a different place. And you can calculate using Newton's theory where it comes back. And unfortunately, it gives slightly the wrong answer by about 10%. So the actual distance that it moves is maybe 10% more. That could be because Newton's theory is wrong, or it could have been because wrong in doing this calculation, or it could have been because actually we haven't seen all the planets or moons or everything in our solar system. So there was many searches that were done to see if there was an object between Mercury and the sun that could explain this discrepancy. There were false discoveries that saw this, but nothing proved that there was anything between the sun and the earth, although it wasn't rigidly disproven by the time Einstein came along. Einstein did not really attack this problem because of the one slight discrepancy from Newton's theory, but rather because of some elements in Newton's theory that basically are incomplete. The first is when we look at Newton's theory, and Newton describes it, we say that we have two objects that pull on each other inversely proportional to the distance they're apart. But notice that Newton never told you why they pull on each other. So yes, we can describe gravity, why the moon goes around the earth, but it doesn't describe why the moon goes around the earth or why there's an attraction. Einstein explains why. And so the first advance in Einstein's theory is to describe why. It's shown in this little picture here. In Einstein's picture, any massive object distorts the space around it. So you can see the space, which would normally be flat here, is distorted by the presence of the Earth. If I put then an object near the Earth, it'll roll toward the Earth. That's equivalent to the apple falling out of the tree or the pull on the moon by the Earth as it's going around the Earth. So the first phenomenon that Newton didn't explain and Einstein does explain, and it's important in understanding science, is why there's a gravitational pull. And that is explained in Einstein's theory by a distortion of the actual space and the time around any object that has mass. The second problem with Newton's theory in some ways was more serious in terms of what couldn't be explained and why Einstein was motivated to find a new theory. And that is that, and this actual deficiency in Newton's theory is something that Newton recognized himself and commented about, but didn't pursue. And that is, Newton's theory basically has instantaneous action at a distance. What does that mean? That means that when the apple falls out of the tree, if we're watching it, at exactly that moment when it's falling, we see that it's falling and know that that's right. And that's true for any of the normal uses of gravity. But when we start talking about astronomical effects or effects that are larger distance, then it becomes a problem. So for example, if I do something dramatic, let's say the sun itself burns out right now, disappears. If the sun were to disappear right now, we wouldn't know it for 8 minutes. And that 8 minutes is because that's how long it takes the signal, this being light, to travel, the light and heat being emitted from the sun, to travel at the speed of light from the sun to the earth. So it takes 8 minutes for us to know that. If we had instantaneous action at a distance, like Newton's theory, then the gravitational signal we would detect immediately. And that's not either logically or physically possible. And so Einstein's theory, gravity or gravitational waves, when we talk about them, travels at the same speed as the speed of light. It's called the speed of light because we knew about that first, but it's the highest velocity that any object can travel at, and that we call the speed of light. So Einstein's theory fixed two fundamental problems. One is instantaneous action at a distance, and the second is why there's a gravitational attraction at all, which is a distortion of space and time. So in simple words, that's basically what Einstein did that advanced beyond Newton's theory. But giving explanations to these new phenomena, or fixing the problem of Mercury, which his theory did also, is not why we would throw away or adopt a theory that had been so successful for over 200 years. What was needed beyond that, and is generally needed in science, is to predict something new that we haven't seen before. And in this case, Einstein predicted that light itself, if it goes near a massive object, will bend because the space around the object was distorted and bent, just the theory of Einstein itself. He also figured out a way to test that, and that is if we look at the sun, and there's a star or stars behind the sun, the light from those stars, if they graze the sun, go beyond, graze the sun, will curve a little bit. And he could even calculate how much. He knows the mass of the sun and so forth. So basically, he predicted that if we could look at objects going behind the sun, we could see it bend. The time when we can do that is when there's a full eclipse of the sun. So the idea that he had is when there's a full eclipse of the sun, look at stars that are moving just behind the sun and see if there's a bend, if they bend like they might. And that was pursued by Sir Arthur Eddington in an expedition to the Southern Hemisphere. And he detected that not only did they bend, but they bent just the amount that Einstein had calculated. And this was a dramatic experiment in 1919, and it is really what made Einstein a household name. So that was the bending of light, which I illustrate here, as the sun goes behind, as the star goes behind the sun, shown here in full eclipse, and seeing that it apparently bent as it went behind the sun. So that was 1919. And this was a dramatic event. This is the article in the New York Times that basically was in disbelief that light would bend. It's pretty illogical to most of us. We know that light basically goes in straight lines. But if you put enough gravitational pull near it, you can actually bend light. That's seen in some other phenomenon and now has become actually a tool of astronomy. So in
Итак,
astronomy,
еще один эффект в астрономии мы знаем о способности света, что он может изгибаться, и, допустим, мы можем использовать изгибающий свет объекта для изучения астрономических объектов. Гравитационно линзированное, так мы это называем. Очень интересно, примечательно в астрономии мы делаем открытия, и с помощью которого мы можем исследовать что-либо. И гравитационное линзирование – это один из таких инструментов. В этом метод гравитационного линзирования.
Так, Алексей, перейдите, пожалуйста, в русский канал. Вы говорите не в том канале.
Gravitational lensing. Einstein's theory then had not only an explanation for the bending of light, which was the second thing. First, it fixed the problems of Newton. Second, it predicted bending of light that was seen. That's a phenomenon that we hadn't detected before, but if we were careful enough, we could see. And thirdly, in 1916, he predicted that there would be gravitational waves. And that was what I'll talk about for most of the rest of the hour. He showed that if you have any sort of object that is shown like the picture here of two objects going around each other. That produces what we call in physics a quadrupole moment. It makes radiation that goes outward at the speed of light, like the radiation of electromagnetic radiation, which comes from a dipole. This comes from what we call a quadrupole. And that radiation goes at the same speed as the speed of light. There's a difference kind of technically, and that is light, when it travels, has with it what we call photons. So we can study it on a microscopic level in terms of photons, or we can look at it in telescopes and see different colors and so forth. But basically, it's explained as having photons along with it. Gravitational waves, in contrast, in Einstein's theory at least, have no equivalent in it called what we might call, instead of a photon, a graviton. We've tested and looked for a graviton in our data, and so far we don't see one. So one of the problems of the future in studying gravity is see if there are gravitons in nature. And so far we don't see any of that. So this is the picture. And we could try to do this in a laboratory, but we can't make strong enough signals. So we basically have studied it by looking in space. So the idea is the following. There is no graviton, so what's going in space, and it distorts any space as it passes through the space. So how does it distort space? I show that in the little picture here. If I have a ring with free masses around it, and a gravitational wave comes through, it'll distort it like the picture I've drawn on the bottom, so that it becomes more elliptical. Since gravity is a wave, it changes each half wavelength such that it'll distort first vertically and then horizontally, then vertically, then horizontally at the frequency of that gravitational wave. However, this picture is fine, but space itself, fortunately for us who live in it, is very, very stiff, you might say. And so the distortion is incredibly small. And that's why it took so long to detect gravitational waves. The size of this effect that we measure is 1 part in 10 to the 21, shown here at the top. And basically, that means if I want to measure this distortion, if it's 1 part in 10 to the 21, and I make a detector that's 1 meter in size, it would be a distortion of only 10 to the minus 21 meters. That's a pretty small number. We can't measure anything that small. And that's what has prompted us to make detectors that are about 1 kilometer in size instead of 1 meter in size. Then we have to measure something that's 10 to the minus 18 meters, which is roughly the size of a proton, or smaller than the size of a proton. So in order to do that experimentally, which I'm not going to talk about very much today, we use a technique called interferometry, and I'm just showing it in one slide and a couple pictures. And it's perfect for measuring a distortion in space-time. Light enters from the left from a laser beam. At the very center of the picture, it splits and goes up and to the right. If the 2 lengths up and to the right are exactly the same, the split light will go to one end and the other end, come back to the same place where it was split in the central mirror, and they'll arrive at exactly the same time. If I invert one compared to the other, they'll cancel perfectly. And so I have a little sensor that senses that. If the 2 lengths are exactly the same, they cancel. If the lengths become slightly different from each other, they don't quite cancel. We see that in our sensor, and that's, in a simple-minded way, the way interferometry works. Only we have to do it at a tremendously accurate level compared to the way it's done in most interferometers that people might be familiar with. We have to be able to tell a difference in length that's 1 part in 10 to the 12th, the wavelength of the light we use. That means doing interferometry itself in much, much more accurately than has ever been done. And we spent years developing that. And secondly, we have to be able to isolate ourselves from the shaking of the earth. It's much, much too big to enable to allow these detections, to allow these measurements. And again, we have to float this over the earth and eliminate any vibrations from the earth at, again, 1 part in 10 to the 12th. And those two numbers represent the experimental challenges that took so long to solve in our detector called LIGO in order to make the measurements. Quickly, this is the detectors. We have 2 detectors in the US, one in the state of Washington called LIGO in the city of Hanford, and one in the city called Livingston in Louisiana. They're 3,000 kilometers apart, as indicated in the center. Speed of light to go 3,000 kilometers is 10 milliseconds. That means if I have a signal somehow coming in at the speed of light from the left side, it will go through Hanford, LIGO first, and then Livingston, and it'll take 10 milliseconds later before it gets to Livingston. Or if I have a signal coming up through Livingston and going to Hanford, it takes 10 milliseconds to get to Hanford at the speed of light. So any signal that I have, if it's detected in both, have to be within 10 milliseconds of each other. If the signal's coming directly down into between them and split them, they would happen at exactly the same time. And we require that, and that's why we use 2 detectors. This is just a picture of the detectors themselves. Hanford, Washington is high desert, and this lives in the high desert of Hanford, Washington. And the second one is in Livingston, Louisiana, which is a big forest with pine trees. They look quite different in the pictures here, but the apparatus is identical down to every piece of electronics. And when we change something in one of the detectors, we immediately change it also in the other detector. So they behave identically to each other. And that means we require that the signal looks exactly the same in both detectors. A strong constraint on both, that the signal has to be there within the speed of light of each other, and the signals have to look identical. Doing all that, we have a sensitivity to see gravitational waves, which is shown in this plot here. Basically, we're sensitive in the same band as our ears, and that's because that's the place where the Earth is the quietest, and we're working on the Earth. The shaded region in the top is a sensitive region. What you'll notice on the left is that the scale has a 10 to the minus 21, the scale that I show, and gets more sensitive as we go down. So more sensitivity is further down. And the shaded region is the region where we can detect gravitational waves. We're limited at the lowest frequencies by the shaking of the Earth still, which falls its frequency to the 4th power. At the highest frequencies, we're limited by what people call shot noise. That's basically how many photons you have in the interferometer. And at the middle frequencies, we're limited by what's called thermal noise, which is the fact that we have some movement of molecules and so forth in our mirrors in the interferometer because we work at room temperature. In the future, we will make the detectors work at cold temperatures. This is then a picture of the actual sensitivity of the apparatus, starting from the top, getting better, curves in different colors, getting deeper and deeper as we made the apparatus better and better, finally getting to the design level that we aimed for. We had to make one very important improvement. We made several before we could finally detect gravitational waves, and that was to isolate ourselves even better from the Earth. The way we isolate ourselves from the Earth is to use shock absorbers like are in automobiles, only much fancier and 4 layers of them. That gave us a factor of 10 to the 10th. If you recall, I said we needed 10 to the 12th. We then devised and made what we call active seismic isolation. That's seismic isolation that includes sensing any movement of the Earth and pushing back against it. So that was done with an array of seismometers and small actuators that actually cancel that movement. So that enabled us to make the detections. This is just the sensitivity that we finally achieved with those improvements, and with higher power lasers and better seismic isolation, it kept getting better and better. And finally, we were able to detect gravitational waves. And this is the picture of gravitational waves as observed in our paper that announced the discovery of gravitational waves. The picture shows the signal on the top as seen in Hanford, Washington, in the middle as seen in Livingston, and on the bottom superposed on top of each other. The scales are 10 to the minus 21, the magic number that I said, on the left scale, and on the right is time. So this, what we're seeing is the evolution of the signal over 0.2 of a second, and the signal getting its biggest when the objects actually merge together. And what you should imagine is these are two objects going around each other, slowly losing energy by gravitational radiation and crashing into each other at the point where the signal here is the biggest. And then there's some little ring down on the right that ends the picture. This was the discovery of gravitational waves. The picture, there's nothing done to this data. In data analysis, it's truly the data itself. Immediately, it looks like what we expect from Einstein's equations using the merger of two objects, in this case, black holes. So if we had two black holes that merge, what we should compare is the top two pictures. The top picture on the left is the same as the one in the first picture that I showed you on the top very left. And that is the picture from Hanford, Washington. On the right is a picture from Livingston in two different colors. In the middle, what you see is the calculations of what the signal would be expected to look like using Einstein's theory of general relativity. And you see with almost no data analysis, just comparing the two, they compare beautifully. And the third panel is the residual, or the difference, if I subtract Einstein's equations calculation from the data itself. And that basically was the discovery of gravitational waves. Using that in detail, we're able to calculate the details of those objects. And this first one already was very interesting. It was two objects, one 36 times the mass of the Earth, the other one 29 times the mass of the sun, the other one 29 times the mass of the sun. Those heavy masses were expected to be very heavy black holes. When they merged together, they gave a final object that was 62 times the mass of the sun. Notice that 36 plus 29 is 65, not 62. So in the actual merger, 3 times the mass of our sun, 3 solar masses, went away, somehow disappeared. And that was in the form of gravitational waves, of which we detected some of it. The rest is the other details that you can tell: how much the final black hole is spinning, how far away it is. It's about 410 megaparsecs, or 1,000 billion light years. And in the right, the calculation of what the masses are. So that was the detection of gravitational waves. I'm just showing you a second one to show you how different they look when we see them at different masses. This is the second event I've ever seen, about 3 months after the first one. And you can see that it had many, many, many wiggles. And The signal, though, was smaller, but many wiggles. And with the many wiggles, we were able to test Einstein's equations with much better accuracy than in the first one, although the first one was better for other things. Since that time, we've detected many more, and this is just a picture of some of the ones that we detected. Down in the lower right-hand corner, and these all are in the apparatus roughly 1/10 of a second, 2/10 of a second. But down in the right-hand corner is a rather different looking picture. You can see it a little bit here. And that is a signal that's